Okay, no starter. I think it's quite a big lesson. There's no starter today. So what we're going to look at today, we're going to zoom straight in. So implicit differentiation, what we did yesterday, but this time I've put using the product and quotient rule, but really we're using the product, quotient and chain rule. I'm just assuming the chain rule is like nothing for us now. So remember, we've got the product rule, and of course, product rule is great. It doesn't matter what way around we write it because you're adding. So it's up to you. You know, we've been looking at it like this or like this. And obviously we've got the quotient rule, which can be written like this or like this, however suits you. Obviously this is less writing and it's absolutely fine. When I've marked exam papers, most of the students are quoting these formulas when they use them. They're just less work. However, in implicit difference, these are really useful, this notation, the dy dx or the y dash, for when you're differentiating explicit functions. Remember, an explicit function is y equals some sort of function of x. To extend these rules to be able to differentiate implicit function, I've got here, we need to rethink this dy dx or the y dash. It's really because we have that in the question. Now, I really like these shorthand formulas for differentiating explicit functions. However, when you're doing implicit differentiation, essentially you really are just using dy dx. Okay, essentially that is, we tend to not use the y dash. So I'll show you what I mean by having to rethink the dy dx, because we can't think of our formulae like this. I'll show you what I mean. So first of all, we're going to differentiate the product x, y with respect to x. Now, it's a product, so I'm going to quote the product rule like that. So the only difference here is I'm just not saying a dy dx equals, because dy dx is going to be mashed up in your answer. So quote which either of these you prefer, essentially, and some of you may already be thinking, having done practice on the product rule, some of you may already be thinking you leave one, differentiate the other, and then reverse it. Add, leave the one you didn't leave the first time, and differentiate the other one. So, but you know, do be careful with implicit differentiation. So I'm going to try and be really organised. So I'm going to let u equal x and v equal y. I know that du dx or u dashed is 1. And of course, I'm going to find dv dx. Now, dv dx, I have to differentiate this y with respect to x. So dv dx or v dash, which is dv dx, you differentiate the y with respect to y and then multiply by dy dx. So this is why it's going to be a little bit ugly. You're now going to substitute these 4 things into whichever formula you like. So you're going to get putting it into the product rule. So you're going to get u times dv dx plus v times du dx. So the derivative of xy with respect to x is x dy dx plus y. Okay, so that's our first example. Example 2, right, it's a quotient. Now I'm going to differentiate this using the quotient rule, but you don't have to. You could rewrite this as a product, and I might actually, you know, I think that might even be a better way to do it, but we're going to do this one using the quotient rule. So you're given the quotient rule. Again, you just have to be mindful because this is not explicit. It's a mixture of x's and y's. So you're going to You know, you're going to think about differentiating implicitly. Now you could write it as a product like this and then use the product rule, but you could, or we're going to leave it as a quotient. So here I am, here's my quotient, and here is my quotient rule. Notice I'm not writing dy dx equals, because that's for differentiating an explicit function, and this is implicit. Either of these are great. Obviously, this is a little bit shorter, more shorthand to help you remember it. So I'm going to let u equal x squared plus 3, v equal e to the 2y. I'm now going to differentiate them. So du dx is 2x and dv dx. Right. First of all, when you differentiate a function in y, remember from yesterday, when you differentiate a function given in y, you differentiate it with respect to y. So the power stays the same, multiply by the derivative of the power, and then you multiply by dy dx. So this is finding dv dx when v is a function of y. And now you're going to substitute it into your quotient rule, remembering you do not say dy dx equals, it's going to be in the mix. So it's looking pretty cumbersome, really. So what you've got here, let's have a look. You've got v du dx minus u dv dx all over v squared. Now, I've spotted that in each of these two terms, so there's one term in the numerator and a second term. That second term is pretty big and pretty ugly. I'm going to, I mean, you may well have got full marks for getting there. I think you ought to simplify that bit there. I think that does, if you're going to leave it like this, you do maybe need to write that as e to the 4y. But what I've spotted is that each of these terms has a factor of 2e to the 2y. So I'm going to, in the numerator, on the left here, so it'd be quite good if I could seal that for a big reveal, I'm going to take out a factor of 2e to the 2y. That's going to leave me, if I take out a 2e to the 2y, so that takes those out, so it's going to leave me an x, and it's going to leave me an x squared plus 3 times dy dx. It's going to leave me those. I've then on the bottom written my e to the 2y. Instead of writing it as e to the 4y, which I could obviously, I've written it as a product because I've spotted this lush little cancel there. So what's going to happen is we end up with something that looks like that. It is ugly. I'm not going to expand that. I could. It would be 2 bracket x minus x squared times dy dx minus 3 times dy dx. I could. And also I could write it as a product. And I think I would have probably got this answer here had I used the product rule. So that's quite a hard question that you've done there. So look carefully at it. Right, even better. What we've got here is a chain rule. So you've got the tan of a function, but your function is given implicitly. Not very nice. So I've numbered these steps. I don't know whether you think that this is helpful or not. I don't know. Well, I'll show you anyway. You can tell me whether you think it's helpful. Right. Step 1. Let's differentiate tan. So let's first of all, I'm not going to use chain rule from first principles because that involves a whole y equal tan u, and then I'm going to use u for something else in my product. So I'm going to just differentiate tan, and I know from my lesson that you did with Mrs. Reed last week that the derivative of tan is sec squared. So my first step is that I've differentiated tan. So I've now got sec squared 3x squared y. So all I've done is differentiated that function. And as you know, your angle stays the same. You're now going to multiply this function by the derivative of 3x squared y, which is implicit and it's a product. So let's take our time. So you can see these are going to be hard questions, big mark questions. So I've let u equal 3x squared and v equal y. I'm now finding du dx. That's great. I'm now going to find dv dx. So I differentiate y with respect to y, giving me the 1, and then I multiply by dy dx. And I now substitute that into my product rule. There's my product rule again. So if I substitute that into my product rule, I get u dv dx plus v, which is y, times du dx, which I've written as 6xy. So that's the derivative. Now I know from step 2, I have to multiply this by the derivative of that. So step 4, here it is. The derivative of the tan of 3x squared y is sec squared 3x squared y times by the whole of this. And if you wanted to, you could, I don't know whether you do, but I think mine's now going to be a bit cumbersome to write it. What you could do, if you know, because there is always that bit of a dodginess about writing the trigonometry first and then multiplying by something, because we're always a bit afraid that you might think you're taking the sec of all of it. So if you wrote it like this, you wouldn't need to put that multiply sign in. Okay, so that you might think is a neater way to write it. Okay, right. Could you now pause the video? And I'd like you to differentiate these implicitly. Okay, so you've got product rule, quotient rule, or product rule if you want. Chain rule and product rule. Chain rule, product rule. Hard. Take your time. Take your time. Okay, here are your answers. So there are your answers. Okay, so you've got your answers there. Trying to be good and doing my X's curly so I can distinguish them between the time sign. There are your answers. Right, moving on. Get ready. A bit harder. Find an expression for dy dx if e to the x plus x sine y equals cos 2y. Great question. Right, so straightforward differentiation, e to the x, product rule, implicit, a little bit of chain rule going on. So let's have a look. This has been taken from the textbook. So if we differentiate e to the x with respect to x, okay, so you split that, what they've done here, if they've just split it up separately, so you're differentiating them all to it with respect to x, we're not doing anything. Right, let's talk about it. If we differentiate e to the x with respect to x, we get e to the x. We're now going to differentiate this product. So this we've let equal u, and this we've let equal v. So in the product rule, we've got u dv dx. Now when you differentiate the sine y, you differentiate the sine y, which gives you cos y, and then you multiply by dy dx. You've now got v du dx, and of course du dx is just 1. So that's our first bit, that's fine. We're now going to differentiate the cos of 2y. Now the derivative of cos is minus sine. So you get minus sine 2y. You now differentiate the 2y, but you're differentiating with respect to x. So you differentiate with respect to y first, which gives you 2, giving you the minus 2 sine 2y. And now you then multiply by dy dx. Now, I don't really like where they've placed that dy dx. I was wanting to put some brackets around there. So that looks a bit, we might really want that dy dx more at the front. So what you're now going to do is simplify everything to make it a little bit neater. And what they've also done here, so they've written this as e to the x plus x cos y dy dx plus sine y equals minus 2 dy dx sine y. They've then gathered the dy dx's on the left, so this has come over and these two terms have gone over there. So that's become minus sine y and minus e to the x. You then take out a factor of dy dx on the left. And now to make dy dx the subject, divide both sides by x cos y plus 2 sine 2y. So what was quite hard about the example they've done there is that they didn't break the product rule down for you. Okay, they didn't say, you know, u is x, v is sine y, and so on. Right, simultaneous equations, big part of implicit differentiation. If there are two different relationships between x and y, and often with our exam questions, which we're really going to look at tomorrow, so we're going to have probably bigger questions tomorrow on this. This is a challenging topic, probably one of our most challenging that we've done in lockdown, I would say. There are two different relationships between x and y. If there are, you use simultaneous equations, and most of the time it's probably substitution, and maybe I should write that. Okay, in most cases we're going to have a bit of substitution. Right, are you ready? Example 5. For the curve with the equation x squared plus y squared minus xy equals 3, find the gradient at the point 1, 2. So before we do anything else, let's differentiate. So the x squared, that's fine. That's just going to be 2x. The y squared, differentiate with respect to y, 2y, multiply by dy dx. Here you have the product. There will be more marks given for this. So let's have a little think about how we will differentiate that product. So there's u and there's v. So if you were going to differentiate the xy, you've got your x, differentiate the y with respect to x, so that's 1 dy dx, plus, you now leave the y and differentiate the x with respect to x, which is just 1. Now, when that goes into the equation, you're going to be taking away the whole thing. So let's have a look and see how the dy dx shapes up. So differentiating everything separately. So as we said, 2x, 2y times dy dx, and then setting this out using the product rule. So I think I'd like to see this. So I'm just going to add a little step in here for you. So you've got 2x, lovely and neat, I know, plus 2y dy dx. Yucks. Minus x dy dx. Minus y equals 0. So that's you having differentiated that implicitly. What you're now going to do, wow, they've just gone for it. They've got the dx's on one side and the non-dx's on the other. So what they've done is they've said, I'm just going to add these steps in because I think it's quite helpful. 2y dy dx minus x dy dx. I hope you're impressed with my pen writing. Equals, take the y over and the 2x over. You're now going to take out a factor of dy dx. So dy dx, and that's going to leave you 2y minus x equals y minus 2x. Oh, maybe if I move that, is that better? Slightly better. And finally, you can go back to the book example. So they were, I think, okay. And you want to find dy dx. Right, let's have a look what they did here. Now what they've done is they've put, because you've got your values of x equals 1 and y equals 2, you can now put them in at any stage, can't you, really? And maybe you could have put them in there. So all you're going to do is you're going to substitute in any of this format. That's the format they've given it in. Any of these, you're going to substitute x equals 1 and y equals 2. So what you could do is you could have rewritten it if you wanted to. And I suppose I kind of like the whole dy dx. You could rewrite it. So dy dx equals y minus 2x all over 2y minus x. And if you now substitute in x equals 1 and y equals 2, you would get 2 minus 2 on the top and 4 minus 1 on the bottom. You're going to get 0. So dy dx equals 0, and you can see in their version of it, when they substituted in, they also get 0. So it didn't actually ask you in that bit to find dy dx. I just kind of like doing it. So, and part B, find the coordinates of the point when the gradient is 1. So let's have a look. When dy dx is 1, so let's take any of the forms that we have with dy dx. So if we use the one that they've got here, all you do is you replace your dy dx with 1. So you end up with this expression. So you just replace dy dx with 1. So now you've ended up with, if you multiply that out, you've ended up with 2y minus x plus 2x minus y equals 0. And that, of course, simplifies to x plus y equals 0. Now, there's an infinite number of solutions to x plus y equals 0, but we've talked about what happens when we have two conditions or two relationships between x and y. So we have this relationship and we have this relationship. So we've got this one, that's a relationship between x and y, and we've now got this one. So we are going to treat them as simultaneous equations. We are going to substitute this one into that one and see what we find. First of all, rewrite y is minus x. So get that original equation and instead of y, write minus x. Don't forget you are squaring the whole of minus x. So substitute that in. So you're going to end up with x squared plus x squared plus x squared equals 3. 3x squared equals 3. X squared is going to be 1. So x squared is 1. So you now square root both sides, and of course it's an equation, so you always have a positive and negative square root. Now if you go back to the question, it asked you for the coordinates, so you need the y value. So when x is plus 1, you need the y value. When x is minus 1, you need the y value. Now by all means, put it back into this really horrible equation here. That would be harder. Or just put it back into your much simpler relationship, y is minus x. So when x is 1, y will be minus 1. When x is negative 1, y will be positive 1. So they're your two coordinates. And sorry, last example, I know they're quite long, but it's good. So find the coordinates of the turning points of this curve. Okay, y cubed plus 3xy squared plus x cubed equals 27. Okay, y cubed differentiating should now feel okay. That's going to be 3y squared times dy dx. Obviously, the minus x cubed is going to be fine as well, minus 3x squared. Here is your product. So you're differentiating them all separately. So be careful with your product rule. So if we think again, that's u and that's v. So u dv dx. So 2y times dy dx, v du dx. And so we've differentiated our product. And there we have our differentiated expression. Now we know that turning points happen when dy dx equals 0. So you could rearrange this to make dy dx a subject, but you don't need to. You can literally just substitute, replace dy dx with zeros here. So 0 and 0. So those terms will disappear. So disappears, disappears. You end up with 3y squared minus 3x equals 0. You're now going to solve that. So you could divide all through by 3. If you divide all through by 3, you end up with y squared minus x squared equals 0. And that factorizes. So you're ending up with y is x or y is minus x. Now remember, relationships. So you've got this relationship connecting x and y, and now, unfortunately, another 2. Take each one separately. So let's consider this one first. When y equals x, substitute that into your original equation. So substitute that in. So instead of y, write x. So you end up with x cubed plus 3x cubed minus x cubed. 3x cubed is 27. X cubed is 9. And what's great about cubed roots is that there's only one answer. So x is the cubed root of 9. And also we know that this is when x and y are equal. So if x is the cubed root of 9, y is the cubed root of 9. Now, we'll try this one. When y is minus x, so you're now going to substitute minus x into the equation instead of y. So, where's our equation? Way back here. So instead, it might be nice, I'm just going to click that so I can see it, what I'm substituting it in. because it seems quite a long time ago we got that. So there it is. So let's substitute that in. So you've got we're actually using y is minus x, aren't we? Y is minus x. So you're getting minus x cubed plus 3x minus x squared minus, and that's not being substituted in, that's fine. So when you gather those together, you end up with x cubed is 27, so x is 3. And of course, this is when x is minus y, or y is minus x, so y will be minus 3. That did feel like a huge question. So, but break it down and follow the logical processes. Right, here are your questions. Take your time, try and be as methodical as you can. And here are your answers. Well done.